We have seen that in the case when two masses M1 and M2 are moving in circular orbits around their common central mass, their positions are stationary in a frame that is co-rotating with an angular velocity equal to the mean motion of the masses. So let's consider now the existence of equilibrium points. There would be a point where a particle P would be placed so that it remains stationary in the co-rotating frame. So this would be the Lagrangian points L1, L2, L3, L4, and L5. Let's focus first on the L4 and L5 and show that indeed these are equilibrium positions for the location of a test particle. So let's consider this system here. You have a particle at a point P, consider that to be the point L4. We don't know yet that this is the equilibrium point. Let's show this. What you know is that there are two forces. One that is directed towards the sun, let's call this F1, and another force that is directed towards the planet. Let's call this F2. The combination of the two forces is directed towards the center of mass. This is the geometry of the problem. You have the force F1 pointed towards the star. Let's say that the vector distance from the mass M1, the star, to the test particle at point P is the vector A. And the vector distance from P to the barycenter, the point O, is the vector B. That's where the combined force is acted. This is the force here, is the sum of F1 and F2. And F2, the force towards the planet, is along the vector C. For the particle at the point P to be at a fixed location in the co-rotating frame, that means that it must be at a fixed position with respect to the center mass. So this force F is actually being balanced by a centrifugal force along the direction of the vector B. So this would be the centrifugal force. So a particle in the Lagrangian point is in equilibrium between the gravitational force towards the sun, the gravitational force towards the planet, and the centrifugal force. Now, knowing the masses, the position of the center of mass is given by m1 times A plus m2 times C over m1 plus m2. Now we can multiply both sides by m1 plus m2. And if you now put all of the terms containing m1 on the left-hand side and all the terms containing m2 on the right-hand side, so I have this relationship between the masses and the position vectors. Now if you now take the vector product of this expression with the force F, because F and B are in the same direction, the vector product of B and F is 0. So this expression then becomes m1a cross F is equal to minus m2c cross F. And I'll substitute F is equal to F1 plus F2. So then what you have is, now you can simplify this expression because F1 and A are at the same line. Therefore, A cross F1 cancels out. And likewise, F2 and C are in the same line. So F2 and C also cancel out. What you have with them is a simpler expression. M1A cross F2 is equal to minus M2 C cross F1. Now, because the angle between A and F2 is equal to minus the angle between C and F1, in modulus, these equations are identical. Now, consider that these forces are gravitational. So F1 is equal to Gm1 over A squared. That's the force directed towards the star. And F2 is equal to Gm2 over C squared. That's the force towards the planet. If you substitute this, you have Gm1 m2 times A over C squared is equal to Gm1 m2 C over A squared. You cut the Gm1 m2s, and you have A over C squared is equal to C over A squared. Therefore, you find A is equal to C. So A must be equal to C. That means that this triangle must be isosceles. So that's not yet the full proof that this is a equilateral triangle. So far, we found out only that this is an isosceles triangle. You have that if the side is equal to A, here between the sun and the point L4, then this side between the L4 and the planet must also be equal to A. What we must show is that the distance D from the sun to the planet is also equal to A. So let's find out how we can prove this. So now is the geometry that we have. We have side A, and the side here, let's call it D, we don't know yet. Let's show that this is equal to A. So let's consider what is going on. We have the force from P to the star, that's the force F1, and the force from P to the planet, that's the force F2. Combine it, they give you this force towards the center of mass that is being balanced by the centrifugal force. Now the centrifugal force, its expression is omega cross r. In scalar form, omega here for this orbit, since it is circular, is equal to the mean motion, and r is the vector b, so the magnitude of the centrifugal force is n squared b. So n squared b must be equal also then to the combination of the forces F1 and F2 projected on the direction of the center of mass. So if this is the angle beta, then what we have is that the centrifugal force n squared b is equal to F1 times cosine of beta. And if this is the angle gamma here, between F2 and the direction passing by the center of mass and the point P, this is equal to F2 cosine gamma. Now, if this forces, then this expression becomes... Well, to advance, let's look at the geometry of the problem here to substitute cosine beta and cosine gamma. From the triangle POM1, we see that if we would take a perpendicular from O to the line joining M1 and P, then this side here is B times cosine beta, and this length is G, the distance between M1 and the center of mass, times the cosine of alpha. So we can write here that A, which is the radius vector here from the sun to the particle, is equal to B cosine beta plus G cosine alpha. And if we play the same game on the other side of the orbit, to the planet, trace a perpendicular from the center of mass to the vector from P to the planet, then this length is B cosine gamma. This side here is D minus G. So this other side here from M2 to this point then becomes D minus G times the cosine of alpha. So therefore A is equal to B cosine gamma plus D minus G cosine alpha. Now cosine of alpha is easy enough to eliminate because this triangle P, M1, and M2 is isosceles. So we have that this distance from M1 to the perpendicular bisector is D over 2, and then therefore cosine of alpha is equal to D over 2 over the hypotenuse, which is A. So cosine alpha is D over 2A. Now from the definition of the center of mass, then we have the little g, the distance from M1 to the center of mass, is equal to M2 over M1 plus M2 times D, the separation. And therefore, D minus G, the distance from O to the planet, is equal to M1 over M1 plus M2 times D. So if we go back to our equation here, we have cosine of beta and cosine of gamma. Let's eliminate them using our expressions. We have these two expressions here. So let's solve the first one here for cosine beta. There is A minus G times D over 2A and over B in both terms. So let's multiply by B. We have then B cosine of beta is equal to A minus GD over 2A. Now let's solve the second one then for cosine of gamma. B times cosine of gamma is equal to A minus dG times cosine of alpha. Cosine of alpha is D over 2A. And substitute the G here, the distance to the center of mass. Now the equation for gamma. And substitute cosine alpha and also the equation for D minus G from the center of mass. Now if we substitute both of these, B cosine beta and B cosine gamma, on our equation for the centrifugal force, let's first multiply and divide the right hand side by B. So now I have B cosine beta and B cosine gamma that we can substitute by our expressions. So this results in, now group together the terms of A, the first and the third, and the second and the fourth. Now extract M1 plus M2 over A from the term in brackets, and we can prove that this term is equal to B squared, so that it will cancel with this B squared. Let's see how that happens. Let's go back to the geometry. We have this triangle from M1 to P to O and back. If you apply the cosine rule to this, then you have b squared is equal to a squared plus g squared minus 2ag cosine of alpha. And because cosine of alpha is equal to d over 2a, then this is a squared plus g squared minus g times d. Now you can extract g from this, becomes g times g minus d, and substitute here now the expressions that we found for g, which is m2 over m1 plus m2 times d, and the expression for d minus g, which is m1 over m1 plus m2 times d. So this expression then becomes a squared minus m1 m2 over m1 plus m2 squared times d squared. And this is exactly what we're trying to prove. So let's get back to our expression for the square of the mean motion. Substitute what is in brackets by b squared. So what is in brackets cuts with the b squared, and you have the usual expression for the mean motion. But the reference frame itself is rotating in the inertial space with an angular velocity given by n, which is given by the distance from the star to the planet, which is d. So this must be also equal to g times m1 plus m2 over d cubed, from which we concluded that a must be equal to d. So this is our conclusion. The equilibrium point for a test particle balancing the gravity from the star, the gravity from the planet, and the centrifugal force lies in an equilateral triangle between the two masses. Therefore, if you have a system with gravitational forces exerted by masses m1 and m2, this system has an equilibrium point at the apex of an equilateral triangle, where the base is formed by the line joining the two masses. This resulted and also implies, of course, that there must exist another point on the other side of the orbit that is also an equilibrium point. These are the Lagrangian equilibrium points L4 and L5.